let me kind of quickly give an overview of what what I did last time and what I'm trying to do here. I think one thing that I really should say about this part of the course is that there should be a big apology for chapters 36 and 37. There's a lot of what I had an idea in mind when I was writing that, and I think it was very much only kind of partially successful. And especially, I think if you try and follow what I'm saying about the relationship between, kind of the classical phase space of solutions of the Schrodinger equation and these operators, these field operators, the language that I was using, I think it ended up getting very confused. So if you're finding that part of the story confusing, that's there's a good reason that it's actually kind of confused in there. But I want to mainly focus on trying to actually get to the quantum field theory. In any case, we're interested in the quantum theory and in these operators. But let me kind of then kind of outline kind of what I'm trying to do and where we started last time. Okay. So let's see. Okay. So what I'm trying to do is I'm trying to get a quantum theory of arbitrary particle systems, and here the point is I want to set up a formalism in which you can talk about states that have an arbitrary number of indistinguishable particles in them. And maybe something else to say that this particular topic that I'm doing is kind of at the basis of kind of a lot of physics. And if you go and look for there's lots and lots of textbooks you can find out there about this is often called many-body physics. I don't know if they want to call it, I think. Yeah, or many-body physics. Yeah. So if you, in terms of the kind of physics of what I'm doing, this is just kind of the simplest possible case of something which is quite important in condensed matter physics, which is kind of the theory of how you kind of talk about a quantum system of a large number of an arbitrary number of particles. The thing that's different about if you look at a condensed matter textbook on many-body physics, you should see some of the same things. There's going to be the same kind of stuff about Fock spaces, about field operators, and all this stuff. The one thing that's different about in condensed matter is typically you're interested in temperature. So in some sense, one way in which what I'm doing is simpler is it's the case in which the temperature is zero. So we're not I'm not trying to also introduce the concept of a quantum system that actually has a temperature that also has a statistical mechanical aspect to it. So we're not actually doing that, and that's what the people in condensed matter really care about. So if you look at anyway, just kind of if you're interested in what you can do with this kind of formalism, as I'm telling you about it today, it's a non-relativistic formalism. So it's not the kind of thing which particle physicists are normally interested in, and it's not the kind of thing which is normally taught in a quantum field theory class. But it is the kind of thing which is often used in condensed matter, except that they're almost from the beginning trying to set it up to anyway. They have some other things going on which aren't going on here. So that just trying to put this in a little bit of context physically. But now, in terms of conceptually, the way that I'm doing this is so the idea. So recall Bargman-Fock quantization. And so the way this worked is you took your phase space or your dual of your phase space, and you threw in complex numbers, and then you made a choice of what was holomorphic, what was anti-holomorphic. You picked a complex structure, and so you and then I forget what I called. And I called then one, and you can break this up into n plus minus, I guess. So you can break this up into, so if you like here, this is the thing that had coordinates q and p, and this is the thing that had coordinates z and z bars. And then what's going to happen then is the quantization is then going to take these elements here. You're going to take to creation operators for each element. In here, you get a creation operator for each element. Here, you get an annihilation operator. They've got certain kinds of the Poisson bracket here becomes the commutation relations for those annihilation creation operators, and the state space which these things act on is this Fock space. So so these, when you quantize it, this is going to act on kind of on this symmetric algebra on this guy, on if you like the polynomials on. Anyway, so you're going to take H is going to be M plus. Okay. So it's going to be the states that you get by taking the vacuum state, and the one quantum states that you get by acting with one creation operator, the two quantum states you get by acting with two creation operators, etc. So this is just kind of a harmonic oscillator story, but for an arbitrary number of dimensions, the harmonic oscillator. So but here the idea, so the new idea is to take M plus is to be H1, what I'll call H1, which is the space of solutions of the three particle Schrödinger equation. Because our idea was that we wanted, instead of describing quanta of a harmonic oscillator, we want to describe arbitrary number of particles, but we want to think of each of those particles as a quantum of some system, and that system we get this way. So one thing that's a little bit funny is maybe just to note is that what I'm doing is that you don't really see in this whole formalism I'm developing here, you don't really see this real phase space M. You see this guy. So this guy is a complex vector space. So this is the solutions to the Schrödinger equation are complex. Again, our complex functions. It's a complex vector space, and you can specify a solution by taking the data at say at a constant time at t is equal to 0. But that's a complex vector. That's a complex vector space. So this is a complex vector space. And if you want to kind of to put this more in this context, then you should think about M minus is H1 bar, which is the space of conjugate solutions. So I can take the Schrödinger equation and then just conjugate everything, which if you like is just going to take that I dt is going to become a minus I dt. I dt has become a minus I dt. And you look for solutions to the conjugate equation, or if you like, just take conjugates of solutions to the original equation, and then you're going to have this different space. And then so you can, if you want to know kind of in this classical version, if you like, what's associated to creation operators, it's for each solution of the, so for each solution, you're going to have a creation operator, which is going to be the thing which creates that solution, which creates a particle that's that solution, a single particle of that solution. And then if you want to know what the annihilation operators are, they're going to correspond classically to conjugate solutions. And so you have, sorry, yeah, so you have this plus this, and you can think of what I was trying to do, and which I'm not going to go, because anyway, because to be honest, just I haven't had time to kind of go back and rewrite some of these chapters and do this better. But you can go back, and everything that we said about the harmonic oscillator story, you can go back and do it this way. Think of these as this guy plus this guy is your complexified dual phase space. The thing that's a little bit funny about the whole Schrodinger story is that you don't actually have, there isn't, what you naturally have is this, because what you're naturally given is a complex vector space. It's not like in the harmonic oscillator thing where your phase space is naturally a real vector space. Here, your phase space is already a complex vector space, and so you take its conjugate, and that's what corresponds to this. I mean, you could try and develop a formalism if you liked. You could try and ask for what are, the things that are real here would be the things that are something in here plus its conjugate in here, and but that actually isn't a really useful notion in this case. Okay, so that's the general idea. Okay, so now the main problem. So the problem really here is that H1 is infinite dimensional. I mean, if you just had a finite dimensional space of solutions in the Schrodinger equation, then you could just precisely take over what we've said about the harmonic oscillator, and it's just be a harmonic oscillator, a simple harmonic oscillator formalism. But the problem is that it's infinite dimensional, so you have to figure out what to do about that. And one approach, which is cutoffs. So you say I'm only gonna but maybe I should say, but they're labeled by. So the thing I should say here about, so you actually know what this problem is so simple because you know exactly what all these solutions are. It's all these solutions are going to be they're labeled by P element of R. Okay, so I'm going to do everything I'm doing today is just going to be for a one spatial dimension, but it's pretty easy to generalize to arbitrary spatial dimensions. And the and so then your solution at time 0, depending on x, is just going to be e to the I px. Or yeah, so it's going to be so these. So if you want to describe this state, the space, this infinite space H1, what you want to do is you can characterize solutions by what they're doing at time 0, because if you know what the solution is at time 0, it's a first order equation that specifies what happens at all later times. And then so you have this infinite dimensional set of possible basis vectors at of possible states at time 0, but we're going to label them by P, this guy. And then the approach with cutoffs is to if you take your space and make it just a fixed size, a so-called infrared cutoff, and then take a fixed kind of minimum distance spacing, then you're basically then you're in a situation in which these guys become discrete, and then what you have is and then Pj is discrete are finite, and you get something like so like an element of you have some smallest possible anyway you take the momentum that's as big as possible but negative, and then you take the same thing and add 2 pi over L. So you have some kind of smallest possible momentum, which is 2 pi over divided by the length, and then you kind of keep going until you get to lambda. So anyway, so you get some finite number of possibilities here, but they're discretized in units of 2 pi over L, and they're bounded by minus big lambda plus big lambda. So one way, I mean, if you anyway, so one way to deal with this is always just to go to this discrete version, and then everything is there's not really any analysis. Everything is kind of purely this is a finite dimensional space. Everything is state space. This is a finite dimensional space. The state space is kind of just the symmetric algebra on it. Everything is kind of finite dimensional and essentially algebraic. Okay, so that's the idea. Okay, but then then what do you do? So when you quantize this, what's going to happen? So this is okay. So what are we? Okay, now, so you can think of an arbitrary element of H1 is specified so the time zero wave function at x, and you can write this as so it's a Fourier analysis tells you x 2 pi p So if I was working with this discrete number of p's, this would then just become a sum, right? But if I start to try to say, okay, well let's try to at least work with a formalism in which we have this kind of continuous number of p's, then what you've got is these are your basis elements, and then these are just the coefficient. These are your coordinates on the space. So coordinates on H1 are I tell them 0p, and I'll call these oh, sorry. Yeah. Or I might want to let me just say that that's fine, and I'll write the notation that I'll often use for these. I'll give these a slightly different name. I'll call these alpha. These functions alpha p.
What does the 0 stand for?
Oh, this is just at time zero.
Oh, time zero. Okay.
Time zero, yeah, because this is all time. Because in general, my solutions are going to depend on time, but if I want to specify a solution, I can specify it by telling you what it is at time zero. So I want to. So this is actually kind of what makes this whole subject a little bit confusing. I'm telling you that I want to quantize the space of solutions. So I need to kind of put coordinates on the space of solutions. So one thing that's confusing is you have what a a solution is going to look like a solution with a fixed p is going to look like p x is is going to be, so a solution with a fixed p is going to be an e to the ipx, and then it's going to have a time dependence, and the time dependence is just going to be e to the minus I times the energy, which is p squared over 2m. So the kind of basic, if you want to think about, what are the basis elements of solutions? What are the solutions that make up the basis elements in this infinite space? Well, they're these guys. But the problem is that how do I okay, so that now and so the claim is that an arbitrary solution is going to be some kind of integral over some kind of sum over the possible p's times numbers. Well, if you want to think about what's going on, it's probably a good idea to just take t is equal to 0, and then just work with the solutions at t is equal to 0, because those are in one-to-one correspondence with a solution with a space of solutions. So you just work with these guys at t is equal to 0, and then you write an arbitrary solution as a sum over these guys with coefficients, and it's these coefficients that are the so this is going to be our so these are our coordinates on phase space, and these are the things which we actually want to quantize. So these are the analog of z in the classical place. So z. So there's coordinate on m plus, okay, or the coordinates. Yeah. Anyway, the basis elements of. Okay, that's what. So the analog of these zj's that were our coordinates on the in the harmonic oscillator case are these functions, and the j, the index j becomes a p. So p is now, this is an indication of the way in which quantum field theory, position and momentum behave very differently in quantum field theory than in quantum mechanics. That here now.
You mean something like c to the power p, something like that?
What that which?
You mean alpha t looks like something like c to the power p, right? A little bit like.
No. It's just I'm saying. So these are the well, I mean, I don't think there's any. So the analogy here is that J is an analog of P, and Z sub J is an analog of the P, and then we're going to have A J dagger is going to be an analog of A dagger of P. I don't know if does this help? I mean, the point is that is that here in the finite dimensional case, there's this finite list of there's this finite set of numbers which index which index your orthonormal basis, which index your coordinates. And that's the J's. So here you're in infinite dimensions, and the thing which is indexing your coordinates are the P's. Okay. So here, here J is now element of some finite set. Here, if I put in cutoffs, P is an element of some finite set. But in general, it's going to be. You really want to think of it as being taking real values. But then the coordinates on this complexified phase space are on the holomorphic part of it are the ZJs. Well, this becomes these alpha of P's where you can. So you should think of, I mean, alpha of P if you want to know, if somebody gives you a solution of the Schrodinger equation, and you want to figure out, what are the coordinates of that solution, well, you find, it's really just these guys. You just Fourier transform the time zero data, and you get some numbers, and those numbers are the coordinates of, with respect to these basis elements. Okay, that makes sense? Okay.
I thought the z sub j's were kind of like the vectors, not the coordinates.
Well, they're they're basis elements of the on this dual space. Yeah. So you're right. I mean, they're coordinate. Yeah, you're kind of on the dual space. So you're looking. They're like q's and p's. You think of q's and p's as coordinates on phase space, or you can think of them as basis elements in the dual phase space. Okay. Yeah. So anyway, so we're in the fact that I'm using kind of curly m means it's the dual phase space. So that's why. So these guys are basis elements here, but they're coordinates on the complexified space phase. That makes sense. You just have to, in your mind, be able to go back and forth between a space that is dual. So here, these guys are. Yeah. So these guys are. Yeah, I guess that's the right thing. That maybe I was saying it wrong. But the right thing to say is that these alpha p's are. You're right. They're basis elements on. They're basis elements on H1. Wait a minute. Yeah, that's right. This was actually part of why I had trouble writing this section. Why I kept on getting confused is because there's this question of how you go back and forth in finite dimensions, keeping track of what's the dual and what's the going back and forth between the space that's dual is not that bad, though it can be kind of confusing. In this infinite dimensional context, yeah, how to go back and forth between the vector space and its dual is kind of the whole core of the problem, because you don't actually, I kind of explained this several times that you, I mean, the problem is you only have that the vector space is equal to its dual when you're in L2, and then but L2 has bad properties, and if you try and go to Schwartz functions, and then the dual is a different, bigger space, and yeah, okay. So this is kind of why this is a confused story. It's exactly maybe because I think what you were asking about, what's the, are we talking about elements of H1, or are we talking about basis vector, or core, or are elements of it, what really are basis elements of H1? They're coordinates on a dual space, but what's the dual here is very confusing. Yeah. Okay, so sorry about that. And that's maybe a good argument about why it's going back to the classical picture is very confusing, and you might be better to just stick to that. In the quantum story, you're just going to have these operators to deal with, and you don't have to worry so much. So you don't have the same problem here when you're talking about alpha. You have the problem of, are you talking about the space or its dual? And here you don't really have that problem. That's gone away. Okay. Okay. So then let's see what else I want to tell you. Okay. Okay, yeah, so then quantization, as I said, it says that these alpha, these kind of, if you like, basis elements of H1 go to a dagger of P, and the conjugates go to A of P. Okay, and these and then what these things anyway, and these both act on the Fock space, which is this guy in some sense. Okay, but the problem with saying this, so if there were a finite number of p's, this would all, and this was a finite dimensional space, this would all make perfect sense. But the problem with just with this notation is that it doesn't really, if you take p to actually be a real number, this is not going to actually, the problem, in some sense, the problem with this guy is if you have a nice well-defined vacuum vector here, the vacuum vector of your harmonic oscillator. If you hit it with this guy, you've created a one-particle state, but you've created a one-particle state which is non-normalizable. You've created this guy, and so the problem is that so then you either have to develop a formalism where you have a Fock space that has all these non-normalizable states in it, but then you don't know how to put the problem with non-normalizable states is you don't know how to put an inner product on them. And so if you want a more reputable kind of thing where your annihilation equation operators are going to be things that don't that create normalizable states, not non-normalizable states, what you need to do is that is you really should think of these as you really should think of these guys as what are called operator value distributions. That they're operators, but they're not. They're things which really should be fed a test function, but before you actually produce them. And so really should work with things which I'll call like a dagger of F, which at least formally is this guy. And then F a Schwartz function. So I'm going to be continuing writing formulas of this kind involving these A and A daggers and similar things in position space. But the right and you really have two ways of thinking about them. You can try and think about what they're doing as things that produce non-normalizable states or annihilate non-normalizable states, and try and make sense of those and try and use those. Or if you want, or you can think of them as that they really have this distribution nature, that they're really objects which first you should pick a well-behaved function like a Schwartz function that that has all the nice properties you want, and then what really makes sense is not actually this, but this, and this what this guy is going and what this guy is going to do is something very well defined on here. He's going to just create a so he's going to create a normalizable state in on here. If you apply him to the vacuum, he's just going to create anyway, he's going to create this state, but integrated against the wave packet F. Okay, integrated the wave packet function F. Okay, so that's the. Oh, and then the Okay, so that's what you're anyway. So I'll kind of go back and forth as I go along, and trying to stay closer to the kind of simple calculations that you often see in physics textbooks, which are kind of where everything is distribution valued, and every so often trying to kind of point to what you need to do to really to make a legitimate statement out of it. Okay, so let's. So I want to tell you about this. Okay, and so then the crucial thing is that in the so I have it go back. So on the complexified phase space. So on M. Well, on the phase space, you have. It says, well, again, let me not go back and do this, but you have a plus all bracket, it's just going to be the generalization. So remember that we had that, what was it, Z and Z bar, I think was I, if I get this normalization right. So it's going to be the same it's going to be the same kind of canonical Poisson bracket on the, except that now you have an infinite. You can think of either a finite number of these coordinates if you have a cutoff, or no limit as some infinite dimensional thing. You have a Poisson bracket which gives you relations. Alpha bar. Okay, now I've forgotten the. I do that. Well, anyway, I've forgotten exactly how I kept changing back when I was doing this. I kept changing back and forth between what was Z and Z bar. So remember, is this I or minus I? We have to. Anyway, well, but it's going to be the same thing here. It's going to be an alpha of P. Alpha bar of P is some. But if we have two of these, there's going to be something like an I and a delta. Then the problem is if these are discrete things, then you get something which is 0 unless P is equal to P prime, in which case it's 1. Otherwise, you have to think of it as being a distribution, as being a delta function. And the and you also have then you quantize. And so quantization, in some sense, is good. In some sense, what this is telling you about is that this is telling you about a you've got a Heisenberg algebra, but it's an infinite dimensional one. And so you're just doing canonical quantization. Says there's only one interesting representation of the Heisenberg algebra, and it's given by these operators, which are P and Q in the either P and Q, or if you like, A and A dagger and the Bargmann-Fock. And so you quantize and you get this, you get these relations. I'll write them out. So these operators are always 0. Let's give you. And the analog of this guy is A dagger. So the quantization. So when you're to go from these classical variables to these, when you quantize, there's always this kind of factor of I and this kind of standard. These standard conventions we're using. So something like, so I guess alpha of P is going to I a dagger of P, and then I forget whether it's a there may or may not be a minus sign there. So I have trouble keeping track of that. But anyway, so up to this I, which is just the. Anyway, this is kind of the standard part of this formalism between. Well, anyway, and you've got but this is where you end up. And now, in order, so this thing, there's two ways to make sense of this formula. One way of making sense of this formula is to say that it really only makes sense for a discrete bit number of p's, for a finite number of p's, and for those finite number of p's, then that this is just 1 if p is p prime and 0 otherwise. But for interpreting as a distribution, what you want to do is this is really saying that. Okay, so there's going to be two integrals. There's going to be an integral over p over a p variable of a function f, and an integral over a p prime variable of of a function g, and that so you're going to get two integrals, dp prime, and you're going to have f. Yeah. Okay. So this guy, I guess this comes out to be yeah. Oh, yeah, that's right. Yeah. So this guy is just going to be a so you're going to have a delta of p minus p prime, and this guy is going to give you a g of p prime, and this guy, and it turns out that this a operator is antilinear in whatever is happening here. So that gives you a bar here. But then if you integrate over p and p prime, there's a delta function here. This is just the same thing as as one integral of f bar of p, g of p, dp. And that's the standard inner product of f and g. So to really, anyway, so what really makes sense is the commutation relations that A's always commute with themselves, A daggers always commute with themselves, and if you have an A and an A dagger, their commutation they actually, to be a well-defined operator on normalizable states, you have to feed them Schwartz functions. And if you feed them each a different Schwartz function, their commutator will be this guy. It will be the inner product of the two Schwartz functions. Okay. Let's see. Okay, so let me go on to the okay. So this was pretty much, again, just what I was trying to tell you a slightly different version of what I was trying to tell you last time. But this is really a formalism where the states are just these symmetric tensor products of these states with a fixed momentum of these solutions of a fixed momentum that you're just talking about some arbitrary number of particles with each with its own momentum, but the formalism is set up where the states are symmetric under interchange, so you can't tell which particle is which. It's like the quanta in a harmonic oscillator. There you can't, if you have two different quanta harmonic oscillator, you really kind of can't tell which is which. Okay, so now, but now what we want to do is we want to go to, so we want a Fourier transform and think about what we want to think about operators which, instead of creating a particle at a given time with a fixed momentum, are going to give you a the idea is that they're going to create a particle at a point. So the problem with this whole formalism so far is that it really doesn't allow. There's no notion of position in it. Everything is just this is all just kind of delocalized particles with fixed momenta running around, and you don't know what if you want to say that I'm going to interact with one of these and do something to it at this point, you don't have any language for that. So so to get a language for that, what you want to do is you want a Fourier transform. So you say define. So quantum field operators are really just what you're going to do is just define. I guess I wanted to say that psi at A or X. What you just do, they're just going to be defined by taking the Fourier transform of and so anyway, so this is just a definition, and again, to make it So again, these are really, well, you have two choices. Either you can think about a world in which there's only a finite number of possible positions. You can set up your formalism that way, or again, exactly, take a cutoff, a size cutoff, and a minimum length cutoff, and just say I've got a finite number of positions, and then so your operators are going to be indexed by that finite number of positions, just like these operators were indexed by the finite number of momenta. And then,
in the textbook, sometimes they define in terms of both A and A dagger. So
in terms of
here,
what?
why is it only? Huh?
In terms of what A and okay. So this is just A dagger, no A and A dagger. Yeah. So you're asking why is it not plus e to the minus I px? Yeah. So the point, this is related to what I'm saying here. So in standard quantum mechanics, you really do have your fields are not real. Your underlying fields are not real. Your underlying fields are complex. That your phase space that you're starting with is a complex phase space. I think we'll get to this later, but there's something that's kind of confusing. If you when you're dealing with relativistic fields, you may want to think about fields which are you may want to think about like the Klein-Gordon equation and look at real solutions and say that you want to quantize the real scalar field. Okay, and if you do that, then anyways, then something different happens. But what I'm saying is that these are inherently complex things, and this is what I was trying to say before. That really, what you've got here is you've got you've got a complexified. You've got a complex. Anyway, it's what I was saying earlier. You've got the complex solutions, or you've got the conjugate solutions. There is no, in the standard non-relativistic theory, there is no interesting notion of real solutions. Okay, you could do this. You could ask, well, wait a minute. What if I don't want to look at complex things and their conjugates? What if I want to look at things which lie partly in here and partly in here, that they're real? That if you conjugate the thing, if you take the conjugate, you get the same thing. Or in other words, what if I try and look at real solutions of the Schrodinger equation? Well, that turns out to not actually correspond to anything useful in a sense. That there's really not if you want to talk about interesting solutions of the Schrodinger equation, you have to look at complex ones, not at real ones. Which is not true in relativistic theory. In the relativistic theory, you do want to look at solutions of a real equation. Okay, I think was that what you're asking about, Leah?
Yeah, when I learned it, it's like, I guess, fully relativistic.
Yeah.
So what about non-relativistic field theory makes it such that the real solution is not physical or interesting?
It's really, I mean, it's just that you're not I think maybe the thing to say about it is more that in the relativistic theory, what happens, you start out the simplest possible. I mean, we'll get to this later, but the simplest kind of relativistic theory is to take the Klein-Gordon equation and look for its real solutions, and then say I want to quantize that. And then when you do that, when you can do that, but when you do that, and you do the same kind of thing, so then you take this to be the real solutions of Klein-Gordon. Then you complexify and you break it up into positive energy and negative energy solutions. So what happens in relativity is you can start with a real phase space. So you can start with real solutions of a relativistic field equation. But what's going to happen is if you to define your vacuum state, to define the theory, you're going to need to complexify and break the solutions up into positive energy and negative energy ones. And the positive energy ones are going to correspond to, you're going to have creation operators. The negative energy ones are going to have annihilation operators. And there's going to be, then you get an interesting, yeah. So what happens in a relativistic theory is, so in some sense, what the Schrodinger theory is what you get if you take the non-relativistic limit of that. So if you take the, do the Klein-Gordon thing, and then you have positive energy things and negative energy things. Well, really, the positive energy things are really the solution, are the solution, you know, in the non-relativistic limit, the positive energy things are just the solutions of your Schrodinger equation. And the negative energy things are just conjugates to solutions of your. Okay, so I mean, you could actually motivate why you have to, you know, why you end up with this picture, why you have to do this by saying that, you know, a more fundamental thing is you can have real fields and you do it relativistically, but when you go to the non-relativistic limit, this is going to happen. Okay, but we'll see. So yeah, so we'll see when we write down field operators that live in here, in M, they're going to live kind of partly in here and partly in here as the real things. And those, then these formulas are going to have two pieces. They're going to have an A dagger piece and an A piece. So you'll see those later.
So I guess in the Klein-Gordon equation, the reason you have positive and negative energy solutions is because it's second order rather than first order.
Yeah, well, that's one. I mean, you have to.
I mean, it factors like in a certain way, but.
Well, you have. I mean, I think maybe it's better to wait till we get to that. I'll get to that in a couple weeks. But it really is a very weird. Yeah, I mean, it's something very fundamental about relativistic theories that they that the way to quantize them is to break things up into negative and positive negative energy. And anyway, so that's just kind of a fundamental piece of structure of a relativistic field theory, which isn't so visible here. But another way of saying it is just that, you know, all of our H1, these are all positive energy solutions. Okay. But if you like another way, I could also think I could change my language and say that instead of looking at conjugate solutions, I want to look at negative energy solutions. You know, okay, so it's the same thing is happening here, but this split of the theory, you know, into holomorphic and anti-holomorphic, or into positive energy and negative energy, is just kind of a fundamental aspect of the whole Bargmann-Fock idea and the whole idea of Fock space and the whole idea that you can think of your states as being starting with a vacuum and then building on them by hitting them with things of positive energy. Yeah, because anyway, so it's just a fundamental structure of the whole theory, and you don't see it so much in you don't see it so much in the non-relativistic theory, because you don't really need to think of these as negative energy things. In the relativistic theory, you actually do need to think about as negative energy things. And another aspect of this, which I'll get to when we get to it, is in the relativistic theory, where life becomes really, really confusing, is if you start with a complex scalar field. If you start with a complex scalar field, then what Bargmann-Fock says you should do is you should complexify your complex scalar field and make it twice as big. So we'll get to this later, but something to look for in almost any quantum field theory book is when they get to when they say, oh, here's what you have to do to quantize a complex field, and they then you've got two things going on. You've got the complex I from the complex field, and then you've got the positive and negative energy thing going on. And so you end up with particles, and you have to introduce particles and antiparticles. And that for the real Klein-Gordon equation, you know, a particle is its own antiparticle. That, you know, introducing an antiparticle is the same thing as getting rid of a particle. They're the same thing. But if you work with complex relativistic fields, then you've got different kind particles. Antiparticles are different. But anyway, I think I better stop now for. Yeah. But anyway, this is so in some sense all that's going on here, I want to say, is we're just writing the Fourier transform. But if you try and make sense of what this is doing, yeah, so it's in some sense saying, well, you know, you're going to go, you're going to create particles with every possible momentum, you know, but you know, weighted by this factor, you know, with this amplitude, and that's but that's going to somehow physically correspond to creating a particle at a point x, but this, as I was trying to say, I think I said last time, this is a physically a bit much trickier thing to think about. Here, these guys, you know, if you create a particle with momentum p, you know, it's going to always have momentum p. It's not going to, the time evolution is not going to be anything interesting. It's just going to pick up a phase factor. This guy, the problem is that if you create a particle at a point x, it you know, x is not a conserved quantity. It's gonna you know, in infinitesimal time, its wave packet is going to go out infinitely far. So this is not a this is a much more physically, this is a much more dubious thing to be thinking about, even relativistically. And you know, I mean, even non-relativistically. Relativistically, people often say that, you know, this has got problems because, you know, you may create particle-antiparticle pairs. Well, here, in non-relativistic theory, the dynamics doesn't create particle-antiparticle pairs, but it's still the whole notion of creating a particle at a precise point at a precise time is a very kind of unphysical thing to do. Okay, and then anyway, so that's then. But this you just define, and then the adjoint is just, yeah, and you define these guys. Yeah.
Oh, actually, for non-relativistic theory, how do they like capture the phenomena? Because I've seen like non-relativistic, but they still have particle and antiparticle, like for different.
Well, there isn't really so the states in this non-relativistic theory. Well, okay. So I was even okay. I was being a little when I was talking about these many body physics. I was simplifying even some more, because the tricky thing about many body physics, about what people are doing then, is that they're often you know, their notion of a vacuum state is often the right notion of a vacuum state is, well, then you have possible holes you can create. Yeah, so they actually have an analog of right, that they have an analog of antiparticles, which is holes in you have some kind of sea of, which is your ground state is actually some kind of sea which you can kind of create holes in. And so yes, and then you have also, and then yeah, then you have to kind of think of those as antiparticles. And so that's another complexity of many body physics, and not really it's another reason why but this formalism, there's none of that. This formalism, there's just the vacuum, and then there's a bunch of positive energy states, which are just all the different, any possible number of free particles running around, and that's all that, you know. So what I'm telling you about physically is something very, very simple. It's not and so yeah, I'm not, my vacuum, my lowest energy state is not some material that I can kind of create that I can kind of create hole. I can create a particle on a hole, and I can't do that here. Okay. And okay, let's see. What do I want to do? Okay, and maybe just to say something quickly about okay. Anyway, then again the same story. So what really makes sense? Makes complete sense. Is SI dagger of F, which is the integral. X, so F, some kind of force. So what really makes sense are actually these operators. And so what you have is, but now just if you just kind of compute, I think I won't go through this, but if you just you could just compute what the commutation relations of these operators are, using the commutation relations of the A and A daggers, and you could show that what is it, that the psi that you get psi of X, psi dagger. Oh, I should put hats on everything. Okay, is that so? The psi's commute with each other, the psi daggers commute with each other, and psi dagger have this kind of commutation relation, and which is in terms of these guys, psi dagger of F, psi dagger of G is the integral of F bar P dx. So it's really the inner product of these guys. And if you're and it's just the Fourier transform the story I told you about these guys, and it's the same story. Okay, so then maybe one thing that might be useful to point out is that you can there's another form, the other formalism you often see when you're first told about that I want to describe a system with multiple particles in it. You're told, well, you can take a wave function, but it just has to depend on, if you want a wave function for two particles, it depends on two variables, on two position variables, and it's symmetric under them. Okay, or anti-symmetric. Oh, and maybe I guess something also that I'm not really saying as I go along here is that everything I say here, you can makes perfect sense if you just make these commutators. So I can interchange. I can. There's a perfectly decent. I can do bosonic quantization of this guy, or I can do fermionic quantization. Either one works exactly the same way, and the only difference in the formulas is just that there's going to be anti-commutators here. But other than that, it's the same. It's really so this formalism makes perfect sense. And there's something about and one aspect of the non-relativistic theory is that it's perfectly possible there the idea of fermions that satisfy the Schrödinger equation makes perfect sense. There's no need to it turns out in relativistic theory you have this kind of relation. Well, anyway, I'll get into that later. But this whole formalism, everything I do there's always a fermionic analog, which is the same formula. Okay, but maybe a good. If you want to understand how to get back to the how to get back to the more kind of standard way, how to relate this language to the language of states of wave functions that depend on kind of multiple position variables, one for each particle. What you want to do is just so you can consider. Well, first, let's just do kind of one particle case. In the one particle case, consider so psi is just psi. If I write this down, I just mean some single particle state, right? And what I often do is I often write x prime is the single particle state, localized with which is a single particle state eigenstate of position. So in the so in some sense, so this is more so in the Schrödinger. So in the Schrödinger picture, well, so this is something like this is really means delta x minus x prime, right? This is the state which is localized at x prime. But just abstractly, I want to think of it. This is a general nice normalizable state. This is this kind of one of these single particle states. It's located at x prime, and then what you do is you always say, well, x prime that you can take the adjoint of this guy and this guy, and this gives you the wave function psi of x prime. So if you want one way of abstractly thinking about wave functions is that they're the pairings between the states and then these eigenstates of position. Okay, but now, but what you could do with this though is you could so note, but you can take what x you can think of what x prime is in this language that we've been developing. This is supposed to be what you would get by doing this. Okay. If you want to, to the extent that this operator makes sense, again, he's going to take a nice state and he's going to turn him into this non-normalizable state. But to the extent you're willing to deal with non-normalizable states, you can think of these guys as good. You can think of these guys as this in my Fox-Bate formalism. So psi of x prime psi. So this guy can also, now if I just take the adjoint of this, he's 0 psi of x prime. Psi. Yep. And then, but this is so this is this guy. This is your waveform. Okay. So one way in this language, if you're just given, you're abstractly given a single particle state, and you want to know what is the actual corresponding wave function corresponding to the single particle state? Well, it's the thing that if you hit him with this operator, and then pair with the vacuum state in Fox space, that's and that's going to tell you what the wave function is depending upon x prime. And you can do this, and then you can do for any number for multi-particle states.
Sorry.
Yeah.
How do we? How's the cat's psi related with the ground state? How can we get the cat's psi from the ground states?
So this psi, psi is just an arbitrary one particle state. Okay.
Yeah, and is there some kind of creation operator to which we acted on the ground state, and then that gives psi?
Well, I at this level, I'm just using psi. I probably maybe should have given it a different name, not even psi. I'm just saying, some arbitrary. I'm just answering the question. I'm answering the question. Somebody tells you, I've got, I've got some arbitrary state, and actually this actually makes sense. More generally, if somebody says, I've got some arbitrary state, it could be anything. It's got any number of particles, any kinds of particles, any momenta, anything you want. And if you want to know what is the, well, maybe better not to say that. Maybe it's better to say that. Let's just say that I know that it's a single particle state. So I've somehow measured something about it that told me that this has only got one particle in it. But otherwise it's arbitrary. Now, if you want to characterize that state by its wave function to get hold of its wave function, I'm just saying, this is how you do it. So this is just lying somewhere in the one particle piece of the Fock space. You hit it with this operator, and you take the inner product with the ground state, and that will give you just form. I mean, that just kind of almost by definition, that just gives you this. So this is just kind of a. So there isn't really anything really kind of going on here other than just definition. Does that make sense?
And just to make sure, like this psi, the zero of the broad zero psi x of x prime, that psi in the middle, that is not the wave function.
Oh, sorry. Okay, yeah. One thing. Okay, sorry. These are the operators. Sorry. Yeah.
Yeah, that's all.
Yeah. Sorry. Yeah. I really probably I got to be careful. What's an operator? And I should have called this. I should have probably even used a different name for this. Sorry, it would be less confusing. Sorry about that. Yeah. I'm saying this in a very confusing way, but maybe make this fine. Sorry. This will make this less confusing. Sorry. That's good. Okay. Does that make more and more sense now? Thanks. Sorry. And fine. Thanks. This is one problem with how I wrote up these notes. Also, I use psi to mean far too many things, and you'll see that I was trying to save myself by making psi and then boldface psi and then boldface psi with a caret. And anyway, so I mean, you'll see if you're trying to read this that you go, what the hell is he talking about? There are too many signs. Anyway, but yeah, this is one place where I definitely was misusing too many signs. Sorry. Okay. But if for multi-particle states, you could kind of do the same thing, and what you can do is you can just say that if you're given if somebody gives you some multi-particle state, which is, let's say, all you know is that this is some state that's got n particles in it, and then what you can do is if you want to know what is the wave function, well, if what I want to do something to this and then produce the wave function x2 xn, and this is then symmetric under interchange. Well, what I could do is I could just do the same thing here. So say of xn xn minus 1 0. Okay. So if I want to from this formalism that I've created, if somebody tells me, okay, that formalism you created is all well and good, but I'm actually unhappy that because the way I like to think of an n particle state is some kind of wave function depending upon n configuration variables that's symmetric under interchange the configuration variables. If somebody tells you that, then you say, okay, well, here's how to get from my states to your representation of them the way you like to think about them. It's just by doing this. And then you find, and then when these things are anti-symmetric, there's anyway, yeah. If these are then anti-symmetric states, there's kind of nice. There's all sorts of fun stories about how to write these things in terms of determinants and stuff. There's a whole kind of formalism for so-called Slater determinants about how to think about how to go back and forth, how to think about things in the language of functions of many variables with certain symmetry properties. But you can get these things out of this formalism by doing this. That's all. Okay, so let's see. Let's see what else I want to tell you today. Okay, so the next thing that I want to do, let me just kind of say a few words about this and get started on this more next time. Or actually, maybe say one more thing about this before we go, which is to say something. So that there's a. Let me just give you the Lagrangian point of view. Okay. So let's say that if you've taken a course on quantum field theory before, and you really wanted to think about it in terms of Lagrangians, you can ask, what's the Lagrangian? Actually, maybe sorry. Maybe let me not start with that yet. Let me just say what I want to say on the next. So the next part of this is dynamics. Even before I start talking about Lagrangians, if I talk about the Lagrangians, I got to tell you what the Hamiltonian is. And so what I want to kind of go back and so the formalism I developed now just tells you about what all these states are, and there's a way of thinking of them in X space or in P space, and there's this nice Fock space representation of them, but it doesn't tell you one of the basic things that you want to know about a theory, which is that if you have a state at a certain time, what is it going to be at later times? And so there's the Hamiltonian. You need to know what is the Hamiltonian operator. So what is the Hamiltonian operator? Okay. So let me just say this. So what we do. Okay. So I think the thing to say is that we so in QFT you almost always use the work in the Heisenberg picture. Okay. So when we, in most of kind of a standard course in quantum mechanics, in non-relativistic quantum mechanics, the way you tend to think about things is you think about the states as the state at some time. The Schrodinger equation tells you what it is at a later time, and you think in terms of time varying states. The basic problem with in QFT is that the states are very complicated to describe. So even in this free particle case, where I've kind of told you explicitly how to construct the states using this Fock space story, a state can be an arbitrarily complicated thing, but here, and this is because the states are complicated, but the operators, the interesting operators are simple, are much simpler. And basically, the interesting operators they're always going to be built out of sorry then. Okay, so they're really going to be built out of these field operators. Okay. And so what we want to so what I want to do is I want to go to a Heisenberg picture and not in the Schrodinger picture. You could talk the way we were talking about these operators. You could just they were just kind of time independent things which operated on your state space. But what we want to do is we want to make these time-dependent things, and we want to say that we're in the Heisenberg picture, and we want our states are not going to evolve in time. These guys are going to evolve in time. Okay, and so again, so recall, so in the Heisenberg picture, so the operators. So if you have an operator at time t, it's going to be given by the operator at time 0, where you've conjugated by the Hamiltonian. So e to the minus I h t e to the I h t. Okay. So the time evolution of operators in the Heisenberg picture goes like this. You take, these are the operators you thought you were dealing with when you thought that the states were time varying. If you want to make the states just stay the same and always be the time 0 state, then you have to make your operators, conjugate your operators by the Hamiltonian this way. Okay, but now if you take the time derivative of this implies that ddt of the operator is, I got this right, is the operator times minus I h. So this is the high, you know, this is the, instead of the Schrodinger equation, this is the Heisenberg operator equation for time evolution. And this is what you want to solve. And so in particular for e.g., so if you want to, let's, you know, sticking to these A of P and a dagger of P operators, you're going to have, so you're going to have ddt a dagger of P is a dagger of P minus I h. Okay, so what's the right? So what's the free particle Hamiltonian operator going to be? Oh, it's going to be. Hamiltonian operator. And again, so the Hamiltonian operator, it's like anything. It's an operator in the theory, and as I said, so it's always going to be built out of A and A daggers, and it's just going to be given by well, let's h is equal to the integral a to infinity of A dagger P A of P P squared over 2x. Okay, so let me I'm gonna stop in a minute here and just let me just kind of try and explain a bit of what's going on here, because this has all sorts, there's a lot of trickiness that's going to go on here. But what you want to do is show, you need to show that a dagger, that this plus this imply a dagger of P and T is e to the I P squared over 2m P A. And the sign goes in the opposite way sometimes here. I'd have to check the sign a little bit, but P and 0. Okay. So in this, what's going to happen is that our if we just think in terms of the dynamics as being associated with the operators, well, as I said, the fact that you know, if you create a particle of momentum P, it just evolves with by picking up a phase like this in time. Well, it's going to be the same thing will work for these. It means that these also have to have the same property. That the way that these operators evolve in time is very simple. They just pick up this phase as you go on. But in order to make sense of this, let me. So what you need to do, and I'll start on this next time because it's part of. It gets into the story which I want to get into. So far what we've done is I've just been talking about operators that are, just A or A dagger or psi or A dagger. They're kind of linear in the basic fields. So the thing about this guy is that he's quadratic in the basic fields. Okay, and so this creates various things you have to worry about because you've decided to multiply two distribution valued fields. Okay, and in general, multiplying distributions is not a good idea. It's not something. It can lead to trouble. But what you have to do is you have to understand what's happening here. I mean, one way to understand what's happening here is to discretize everything. To just work with a finite number of p's, and turn this into a sum, and then then do this calculation and use the commutation relations for A and A dagger of these discrete number of p's, and you can get this answer very quickly. So that works easily. If you try and think of this in terms of distributions, then it's trickier because you have to you've decided to multiply two distribution value things, and that's so this is kind of what I want to spend some time talking about next time. Is about what are the we had this whole kind of theory we developed about symmetries and quadratic operators in the case of the harmonic oscillator. Well, we're going to need that. A lot of those, we're going to need those same kind of quadratic operators, but in this infinite dimensional context here. So I'm going to, anyway, so this is where I want to start next time. But the thing to say here, I guess, is that yes, I mean this is though the, if you can make sense of it, this is the free particle Hamiltonian. If you want to get into more interesting systems, some more interesting systems that are nonlinear are ones where you're going to add, like if you add terms to this that are higher order than second order, then you're going to have some nonlinear theory, which can do where arbitrarily complicated things can happen, and then you need the full formalism of perturbation theory if you're doing calculations or some other way to do calculations. But anyway, but this again, we're sticking to the free particle theory. This is the Hamiltonian. You can anyway. So next time I'll say some more about this. And one of the first things to say about this is to think about what happens when you Fourier transform it. When you Fourier transform this formula, what is this in terms of psi and psi dagger? And maybe we'll start with that next time. Okay, so let me stop there. Okay. So are there any questions about this stuff?
Just one quick question.
Yeah.
I know it doesn't matter much for the classical theory, but I noticed that you switched signatures from 1,3 to 3,1, where before you were writing TX, and now it's PT.
That's just purely random inability of me to keep track of which order to put time. Or I think you'll find that when I write. Okay. Yeah, when I write time and space, the dependence on time and space, I can never think of a good reason to put time first or space first, and so I kind of randomly do whatever happened to. And you're lucky if I don't change my mind in the middle of the calculation. But yeah, no, but that it has nothing to do with it has no physical significance at all.
Okay.
Yeah. Okay. Sorry. Anything else right now? Okay. Anyway, so if not, do I'll shut this off and do come back soon. I'll be around for a while. Bye now.
Thank you. Bye. Thank you.